we're working on chapter 9, so we are jumping ahead in the book. So we went from chapter 5 and it took a nice close look at the sun, our closest star, as sort of our reference, looked at many physical properties of the sun. Now we're going to jump ahead to chapter 9, which is the family of stars. So we are branching out in the universe and going to take a look at the family of stars. It has very interesting characters in it. And so our little what are we summary is that we are medium. But we do live between the microscopic and the astronomical scales, as we mentioned before. And so yes, we do sort of have a medium experience here. But when we start to look at the family of stars, we also see that our star, the sun, is rather medium. It's not the largest star out there, and it's certainly not the smallest star out there. So we do want to look at our family of stars. So this chapter is going to concentrate on 5 basic goals here, trying to find out how far away the stars are, that ever important unit or property of distance. And we gave you a little bit of that when we were looking at the distance of the sun and how we could use that in some calculations. We sort of have what we call an extragalactic distance pyramid looking thing. It's a ladder, we call it, that I'll be sharing that with you. How much energy our stars actually do emit. We looked a little bit about last time the apparent brightness of stars, just how that looks to our naked eye. Very subjective, right? So now we really want to look at what's going on with the amount of energy that they are emitting, what their surface temperatures are. And so we started a little bit with some wavelengths and introduced Stefan Boltzmann's law and Wien's laws that related temperature in there and energy and wavelength. And so we'll be taking a look at that and how we can use that to sort of classify stars, their temperatures, how big they are, what are their diameters or their radii, and then how much mass they contain, so how much matter is actually in them. And there is a wonderful diagram that sort of puts many of these properties together in one nice diagram. So we'll be taking a look at that Hertzsprung-Russell diagram, sort of summarizes many of these things. Okay, so distance is a very important unit, and also the most difficult. Astronomers do use many methods to get at the distances, and of course, as those distances become larger and larger, they use different methods. So something that might work for maybe the distance to the sun or distances between planets, that might be one method versus here we are going different distances between galaxies. And so we will kind of go up this extragalactic distance ladder as we progress throughout the semester. So I have one available on Blackboard for you, and I'll keep putting it up underneath the camera as we go through. So kind of you can use a little geometry, a little trigonometry, really, much like the method that surveyors use to measure, say, the distance across a river that they can't, cross. We can kind of look at that and then be able to apply that to our stars. And so basically, see this triangle that they are able to survey and connect up. You're kind of mapping out a triangle here, right? Using your trigonometry of angles of a triangle and being able to calculate then a distance in that manner. And so this is sort of the basis of how we do kind of use that triangulation method and use this for astronomy in getting distances. So there is a similarity there, but basically we're interested in an angle known as parallax, and I know I've introduced that term to you several times, but parallax is sort of that apparent shift, apparent angle of movement from the observer's motion. So let's say we could take a photograph of a star, okay, one position of Earth in its orbit, and then 6 months later, as the Earth has gone a little further in its orbit around the sun, we would go ahead and take the picture again of that same star, and we would notice a little bit of a shift, an apparent shift that kind of occurred. So we could examine both the photos, and that the star is not exactly in the same place in the same photo. So there's that slight little shift, that little angle we call parallax. Okay. So we do have sort of a, it's looking like the triangle that they used for that surveyor's method of that river they were trying to get the distance across. But here is d, distance, okay? And we can use a little equation, and that's the parallax, that little angle, okay? So there is a relationship for that. Let's see. Again, you're not going to have to calculate these, but sometimes it is nice to see that relationship, where d is the distance. And p equals parallax. Okay, that small little shift in there. And so a very small parallax, right, a very small shift in angle would indicate that you have a very large distance, because notice the inverse relationship there, okay? So very small parallaxes indicate to you that your distance is very large. And if you remember, I think it was way back in chapter 3, I think, when we were mentioning Tycho Brahe and his new kind of star, it was now called Tycho supernova, and he was saying how he couldn't get the parallax on it. So that had to indicate that it was a very small angle. He just wasn't able to calculate it because of his technology at the current time. Indicated that it was a very large distance. And that put into the works of, kind of thinking outside of the box. Got us started there with Tycho. But this is the idea. So this is known as stellar parallax. So actually just observing the stars over time and getting at the parallax there. And so that's one method that we do use. I'm going to put my little extragalactic distance ladder under there, because that's one of them that they do mention. And there are many on here that we will be getting to as we continue our study. Of course, radar ranging, of course, from the Earth basis, but the next run, so for distances about 1 AU to 200 PC, which stands for parsec, if you remember that unit. But this method here, see the triangle? So triangulation kind of method using stellar parallax, and so that's what that rung is. And so these different methods are useful for when our distances do change on us. Okay. So the parsec, though, and these other ones we're going to, again, I'll keep popping these under here, but spectroscopic parallax, variable stars, Tully Fisher, supernova. There'll even be another one that we'll introduce when we study the universe as a whole. But as we progress through the semester, our distances are going to become much larger, and so we have different means of getting at distance, different methods that are used, okay? So, and that parallax, okay, common kind of apparent and shift of a position, the thumb thing where you're looking at your thumb from this eye, close that eye. The thumb, if you try that out at home, your thumb does look like it's moving because it's really because of the distance, okay, between your eyes, your viewpoint, right? So it does look like an apparent shift. That's a parallax, okay? Of course, if you were to hold your thumb even farther out, that shift would be smaller. So the premise is the same when we're looking at the stars as well. So there is sort of this commonality here on how we can get at a distance by measuring that parallax. Okay, so the stellar parallax. Okay, so these can be very small though. Like Tycho had a little trouble finding his, but some of these distances are so large, right? It's parallax small, so you get extremely large distance. There's that new unit. So we had astronomical unit, right? Average distance between the sun and the earth, 1 AU. Well, now when we're having distances that are very large, right, and you measure them via the parallax, it's actually better to use a more appropriate distance known as the parsec. And that word is kind of combining parallax and arcsecond. Okay, so parsec. They combine those two words, but yeah, the parsec equals the distance to an imaginary star, right, that has a parallax of exactly 1 arcsecond. And so again, an arcsecond is just this fraction of a degree of an angle, right? It has nothing to do with time. So 1 degree is 60 arc minutes, and 1 arc minute is 60 arcseconds. And so it's a very small kind of fraction of that. So and then remember, we did give this to you before. A parsec is 206,265 AU. Okay, so if you're thinking that distance between the Earth and the Sun, go ahead and 206,000 some odd, greater than that, or roughly 3.26 light years. Okay, but parsec is really nice to use with parallax because it does stem from that. Its definition stems from distance to an imaginary star that has a parallax of 1 arcsecond. So it is related directly there to the distance. So yeah, so trying to get at distance using parallax, okay, and they've come up and produced several catalogs with parallax, so 120,000 stars, something like that. So trying to catalog the distances of these. So difficult to get at, but that is one method, stellar parallax, and we'll be looking at more as we go through. Okay, so we've already introduced to you the apparent magnitude, or that apparent visual magnitude, so that little m sub v, if you remember that, and that one is how a star's brightness looks to us, just to our unaided eye. Okay, could be very subjective. Honestly, but in order to figure out the true nature of a star, okay, we need to know its intrinsic brightness. So intrinsic brightness, okay, so remember that little m sub v, we'll kind of put that one down. That's sort of the apparent visual magnitude. Just how that looks to our eye. Then capital M sub v, okay, is the absolute visual magnitude. And the sub V is standing for the visual part of the electromagnetic spectrum, okay, just the visual portion. Okay, so this one here is very subjective. You know, the apparent visual magnitude could vary so much that, you know, you really don't know intrinsically how bright your star is, how much energy it's actually putting out, because distance is a factor. A star that might look, so its apparent visual magnitude might be very bright to us, but it just might mean that it's closer to us. We could have a very bright star, intrinsically bright star, absolute visual magnitude, be very bright, but yet it looks faint to us because it's very, very far away. Okay, so very far away, it looks dim to us, but it could intrinsically be putting out quite a bit of energy. Okay, so this absolute visual magnitude helps us get at intrinsically how bright is that star, how much energy is it putting out. Okay, and again, it's in the visual portion of the spectrum. So to know the intrinsic brightness, we really need to know, that's a measure of how much energy output is being put out. So here it's saying intrinsically very bright stars might appear faint if they're very far away. Okay? It could really actually be producing a lot of energy, but we can't tell it because it's so far away from us. So you see the problem there with the apparent visual magnitude. So we do like to use absolute visual magnitude. And kind of its definition, it's kind of weird how they call this, but let's see if we can get it up here. Well, the definition of it for this one, the absolute visual magnitude is what the apparent visual magnitude of a star would be if it were put 10 parsecs away. So what we're trying to do with that definition is we're trying to put all the stars 10 parsecs away and then compare them as far as their brightness goes. So we took away the factor of distance. That's the problem with the apparent visual magnitude scale. And so in the absolute visual magnitude scale, okay, this would be the star's brightness if it were at 10 parsecs away. Okay, so we're trying to put all the stars on the same playing field right there at the same distance and then look at their brightness. So that's what we're getting at with the absolute visual magnitude scale. It's a much better scale because then that tells us what's going on intrinsically, the intrinsic brightness of our star. So that flux of energy in joules per second, okay, actually how much energy is coming out is what that's all kind of tied up into. Okay, so yeah, distance does affect your apparent brightness. Yeah, so the brightness depends on its distance. So to know the apparent brightness of a star and its distance from Earth, we can use the inverse square law to correct for that distance, right? So again, it's an inverse square kind of relationship. The farther away the star is, the less bright it's going to look to us. So that kind of inverse type of relationship. So that's the problem with our first one here. Okay, distance can affect that. But here, if we use that 10 parsecs as the standard distance, we're putting all the stars, using our imagination here, to put all the stars at 10 parsecs. This is referring to intrinsic brightness, the absolute visual magnitude, capital M sub V, okay, on this. So, and again, the V is just for visible light, okay? Just that little portion of the electromagnetic spectrum for absolute visual magnitude, okay? Okay, so another brightness kind of indicator here, absolute magnitude, is what we call luminosity. So visual magnitude, that is only the visible light spectrum. We want to know about all manner of electromagnetic radiation, and so luminosity, there, our term for that. So there's a lot of radiation that we can't see with our eyes, right? We can only see in the visual, but there are, the ultraviolet rays, shorter wavelengths than the visible light, and infrared waves and wavelengths that are longer than the visible light spectrum. So we want to know all of this. So we do want to get the whole thing, and so that is what luminosity can do for us. Okay, we can find the total electromagnetic radiation energy output of a star by looking at luminosity. Okay, and so luminosity is looking at the entire electromagnetic spectrum and how much energy is being put out on that. But It's really based on the temperature of your star and the diameter of your star. And so we'll be looking at that a little more closely here in just a bit. But there's an equation type relationship that I'll show you with that, comparing temperature and its diameter, okay? That'll become important to us. Okay. So let's take a look here at the temperatures of stars. It comes down to these spectral lines. If you remember the spectra, the little spectroscope that I showed you last time, where those spectral lines, okay, we can take a look at those, and they can be very sensitive as sort of a star thermometer, okay, because we can take a look at the lines of each atom. They're strongest at a particular temperature or wavelength, right? And so here across the bottom, we've got several temperatures, okay? 10,000 Kelvin there, 6,000 Kelvin, and then 4,000 Kelvin. And then these are the line strengths from low to high. For various, they've got some ions in there. Ionized helium is one. Okay, that line. Helium here, hydrogen is red one. What do we got? Ionized calcium here, ionized iron. We've got a compound, titanium oxide. So just some various substances, and where their temperatures are their maximum intensity. So relating a wavelength to a temperature, when we can do that. Remember Stefan Boltzmann and Wien's laws helped us relate wavelengths and temperature and energy back in chapter 5 with that. So hydrogen, okay, a maximum intensity, a line strength, so a spectral line strength around a 10,000 Kelvin. So the hydrogen ion, little electrons are buzzing around and being very excited at that temperature. So you're going to see a very strong spectral line in your spectra, that is, at that temperature for hydrogen. And then it kind of wanes as the temperature cools off. And so you can kind of look at many of these different little ions and molecules and use it as a sensitive star thermometer. So some of the colors, and we've already sort of done this with looking at Wien's law, but where temperatures and wavelengths kind of go hand in hand, where very hot temperatures would be very short wavelengths, so an inverse kind of relationship. So those would be the blue stars. So a hot star would be looking to us a hue of blue, and we could tell, well, that's a very hot star, compared to a cooler star. And again, we are talking about stars, so they're still pretty hot, but in comparison, a cooler star would have sort of a red hue to it. So reds are longer wavelengths, right? So longer wavelengths have cooler temperatures, and so sort of that inverse relationship, that Wien's law of temperature and wavelength, but also colors being related to that. So bluer stars are hotter, shorter wavelengths. Cooler stars are red and have the longer wavelengths. So kind of that relationship. So red stars are cool and blue stars are hot. Okay, so spectral lines and temperatures. So the spectral lines relate to the wavelengths that they're emitting at. So Kelvin, again, is what we're using. So typically stars have just a few thousands or maybe tens of thousands of degrees of Kelvin. The centers of the stars may be many millions of degrees Kelvin. So there is sort of a difference throughout the star. Various regions have different temperatures and various different things are going on within those sort of layers of our stars. We'll find that out later on. But this is still relating the lines on the spectra with the temperatures, okay? And so here, if you remember, this is our Balmer series of the hydrogen atom, absorption lines in there. Remember that Some of those were in the visible light range, so there was a sort of a blue and a red and a violet that we could actually see. There were 3 Balmer lines that we could see because they were in the visible light region. And also there were some in the UV, which our eyes can't see that. But from these different absorption spectrums, so depending on whatever the temperature was doing, was that a right amount of energy to bump them up and excite that electron and then have it fall back down to the ground state? So specific things will happen at specific temperatures, and we can take a look at those spectral lines and know something about the temperature of your star. And so that's kind of how the spectral lines relate to temperature. Okay, very nice. And so we have some astronomers that study this. Let's see, Cecilia Payne, if you remember her, we've mentioned her before, where she was able to look at the spectra and actually identify different elements, composition of our stars, if you remember her work, okay? Because of whatever was going on with spectral lines, okay? But you could also do this with temperatures as well. And Annie Cannon was another female astronomer and that did help us put together sort of a spectral class of stars based on their spectra and the temperatures that they were emitting at these. So yeah, each line of the atom molecule is strongest at a particular temperature. So hottest stars are, you know, about 40,000, coolest are about 2,000, again, Kelvin. And then the sun, our sun's about 5,800. This is sort of the average kind of surface temperature of the stars. And so, yeah, we can get some much hotter and some much cooler than our star, the sun. So we, again, we're medium in there as far as even temperature goes. So here we have the spectral classes. This would be table 6, well, this is 6.1. It's actually 9.1 in your book. I think I mentioned before that these PowerPoints are actually from an earlier edition. They sent me the new edition book, but not the new PowerPoints to go with it. So know that that should be 9.1 for the table number on that one. So here we have, according to what's going on with their temperature, what's happening with those hydrogen Balmer lines. Here we've got some other spectral features such as what was happening with ionized helium, neutral helium, the calcium in there, so various other atoms in there. And then some examples of naked eye actual stars for that. So here you're seeing some letters on here, an O star, spectral class of O, okay? And there's a B, and then an A, and an F, and a G, and a K, and an M. Letters. So we need to memorize these letters. Okay. They don't mean a whole lot, but if we could put a little mnemonic with it, you might be able to remember it a little bit better. So let me write up something here. This is the spectral class. Okay, so here's one. I mean, they come up with a few others, but I happen to like this one for our spectral classes. So O, B, A, F, G, K, M, and the little mnemonic is O, be a fine guy or gal, whatever your preference, kiss me. Okay, so O, B, A, F, G, K, M. So O, be a fine guy or gal, kiss me. So maybe that'll help you remember your spectral classes. I hope so. Or make one up on your own, whatever you will remember. But our O stars, okay, are the hottest, okay, on this end. and our M stars are the coolest, okay? So they are stemming from those spectral lines that, according to temperature, okay, what their spectra look like, okay, and then we're assigning a letter to it, and this has been modified over the years to where, you know, it's been reduced down to these spectral classes, and you can also get little subdivisions. They'll show us that in a bit. But the hottest are the O stars, a little cooler B, a little cooler A, and so on to the coolest M stars on that end. And they've actually added a few others that we'll talk about a little later there that are even cooler, but objects that are cooler, not necessarily that they're stars. Okay. All right. So that's the premise of our spectral classes. Okay, 7 main spectral classes. Just gonna have to memorize these. But Annie Cannon, right? She personally inspected over 250,000 stars, looking at their spectra. So tedious work. But thanks to Annie, yes, we were able to bring together this spectral class, okay, based on the appearance of the star spectrum, okay, and relating that then to the temperature. Okay. And so this set of stars is called the spectral sequence, and it's important because it is based on their temperature. And again, I mentioned that there are some little subdivisions. So for example, say a class A, spectral class A has some little divisions, A0, A1, A2, bring that back here, and so on to A8 and A9, okay, and then next would come the F. Okay, so they do kind of sub these into about 9 little divisions, and then there you go. And so A9 is a little bit hotter than an F0, right? Because this direction's getting cooler. So yeah, your little subdivisions in there to really try to fine tune and pinpoint a better temperature in there on this scale. So here's the sun. The sun is a G star, kind of in the middle, so medium again. But it's more than just a medium G star, it's a G2 star. Okay, so a G2 star, okay, somewhere in between there a little bit. And its surface temperature is 5,800 Kelvin. We mentioned that just a little bit ago. So here's some mnemonics that they use. Maybe you like these better. It says, oh boy, an F grade kills me. We don't like talking about F grades. And here is one, only bad astronomers forget generally known mnemonics, and mnemonics actually starts with an M, so you have to remember that. Or, oh, be a fine guy or gal, kiss me. Whichever one you prefer there, or you could certainly make up your own. But spectral classes, L and T, as I mentioned, you know, they kind of add a couple even cooler objects that we call brown dwarfs. We'll talk about those when we talk about our star deaths. We'll have more to say about that. But here, this is kind of color-coded, right? The blues are the hotter, transitioning to the greens, to the yellows, and the reds, off to the longer kind of wavelengths, so cooler end of the spectrum. And you would kind of set up temperatures of stars that your reds would be the coolest, and then you get towards the yellows, like our sun, sort of a yellow-orange color, right? Kind of out here in the medium. That'd be an intermediate temperature. And then blue stars are very hot stars. Okay, so colors and temperatures can be related. And so spectral classes helps us with that. Colors, wavelengths, temperatures, all of that wrapped into kind of one thing here. So really, and astronomers don't really look at the color-coded things. If you remember that, they're interested in the little graphs here that you see. And so yes, these wavelengths of maximum intensity is in the infrared region for the coolest stars, which makes sense because infrared is a longer type of a wavelength. And the maximum wavelength of maximum intensity is in the ultraviolet range for hotter stars, right? Because the ultraviolet wavelengths are shorter, and that would be hotter. So that does make good sense. And so they are looking at wavelengths. I know you probably can't see this, but you should have these PowerPoints that you can examine. But here's a very short wavelength, 400, then we get longer as we go this way. This is 700. And so depending on where their wavelength of maximum intensity is lying in wavelengths in nanometers here on this one, we can figure out temperatures just from the spectra. So amazing information that these spectra have given us. Okay, now we want to look at the sizes of stars. So what's going on with their diameters? We have some stars that are very similar to the sun's diameter, some that are much smaller, some that are much larger, and so we do have variation. But how we can get at diameter is through that term we mentioned just a little bit ago, luminosity. So luminosity does have a relationship that will help us get a better understanding of the diameters of our stars. So luminosity, let's see. The star's luminosity is proportional to its surface area. Okay, so luminosity. Here should look familiar. That's the Stefan-Boltzmann law, portion of the Stefan-Boltzmann's law. Right? And this is surface area, formula for surface area. So luminosity is related to temperature, right? T for temperature. And you see the R in there, that's a radius, which if you know your diameter, radius is half of the diameter. So we need diameter and temperature. If we get those two things, we can calculate the luminosity. Okay, so that output of energy at all wavelengths. Okay, so all the luminosities there. So surface area, temperature, and surface area, and this is luminosity. Okay, that we can get. We can do a little calculation for that. That will tell us something about surface area, diameters, so sizes here of stars, and their temperatures as well. So we have this diagram I mentioned at the beginning, the Hertzsprung-Russell diagram. Two gentlemen that were able to put this together. So they're both kind of names are incorporated there. But it separates the effects of temperature and surface area on stellar luminosities, and so it's really interesting. It can get pretty busy. It has a lot of information on it, but it separates the effects of temperature and surface area on stellar luminosity, and it enables us to sort the stars according to their diameters or their radii, okay, because that's half of a diameter on that. Yes, so here's two gentlemen that each separately came up with this, but yet they're both getting credit for it. Okay, and you can also, in this diagram here, get to it there, put those spectral classes that we had up there. So you'll see that on the diagram. So there's the O, V, A, F, G, K, spectral classes, right, that had something to do with the temperature, right, of the spectra. And here's luminosity, L. Okay, so going to 1 here. And anytime you see a symbol, so they have the L, like this, and then they have a little circle with a dot in it, that means they're referencing the sun. Okay, so the sun luminosity would be L, would be a 1, and then we compare and reference everything else to what the sun is. So as we're going up, there's 1 there, 1 times 10 to the 2nd, 10 to the 4th, 10 to the 6th, and then now we're going smaller, 10 to the minus 2, 10 to the minus 4, so less luminosity at the bottom of our table to greater luminosity on the upper part of the scale there. Over on this side, see the M sub V, capital M sub V, so absolute visual magnitude. A lot of times it's also separated with that, so that's on this side. And across the bottom is temperature in Kelvin. So we've got 30,000 over here, Kelvin, 20, 10,000, 5,000, 3,000, 2,000. So temperature in Kelvin across the bottom. And also look at it, it's color coded. So visually you can just see that over here we got our blue stars. So that's the very hot stars over here. And then in the middle we've kind of got the whites, the yellow, the oranges, okay, in there. And then your reds kind of towards this end. The cooler stars are down at this end. So very colorful, color-coded based on those temperatures, right? And then now we're throwing in luminosity, so we can tell something about the radius, the diameters. So radius is also on here. Right along here we've got what 1, let's find it right there, 1 R, so R with this, okay, that's what the radius of the sun is. Okay, and so that's this one. Notice how this goes from the upper left and kind of slants down toward the lower right. So those lines there have to do with the radius of the star. And so anything along this line here that happens to be on that line there is the same radius as the sun. Okay? All right. These lines up here, so here we have a radius of 10 times the sun. 100 times the radius of the sun, 1,000 times the radius of the sun, so much larger diameter stars. And now down here we have 0.1 radius of the sun, 0.01, and so here we've got really smaller radii than the sun. But notice how they slant from the upper left down to the lower right of our diagram. That would be the radius lines in there. So lots and lots of information going on in our spectra, or in our diagram here, our Hertzsprung-Russell diagram, but always comparing to the sun, okay, that medium sized thing. But here I have something that's a little more stripped down so that you can maybe see it, that it's not so busy, because they've put in a lot of other names on there, kind of categorizing stars according to their sizes and their temperatures, their luminosities. And so let's just strip it down here and take a look at the bare shell of it. So here we have luminosity, right? The sun would be 1, right? And off over here, these dashed lines, as I mentioned before, are the radius. And so 1 R with that little circle and dot, that would be the sun's radius, and anything on that line would have the same radius as the sun, right? And up here, 10 and 100. So I'm really stripping that down for us as far as luminosity, what's going on with the radius here. Here's the temperature again across the bottom, those spectral classes, O, B, A, F, G, K, M, G, K, M, okay? And that's based on their temperatures. 30,000, so the hotter stars are the O and the B's. O is the hottest. And we get cooler M, the coolest stars down here. And it's color-coded as well for us. So then I'll add kind of an overlay here where it's putting some stars into some groups. I hope that's showing up for us on here. And so the majority of the stars, probably 90% of the stars, are on what we call the main sequence. So this sort of, it looks like kind of like a slipper slide here. Okay, starting way in the upper right, or upper left, sorry, and working its way down to the lower right kind of corner there. Those are known as the main sequence stars. Okay, main sequence stars, a star will live the majority of its life on what we call the main sequence. And so this is doing normal star things. It's fusing its hydrogen into helium. That's what the definition of a star is, when they can actually fuse their hydrogen into their helium in their cores. That's a normal function of a star. And so 90% of their life, they are on the main sequence doing normal star stuff. Okay. So the majority of the stars out there are main sequence stars, okay, because they're living most of their life on the main sequence. And so that's what we call the main sequence. Now if we look up here, we see the term blue giants. And so they're getting that term giants in essence is because they're much larger than our normal main sequence sun-sized star, okay? So their radius is much larger, okay? And so it's called a blue giant. We even have blue super giants because it goes to the diameter or the radius of the star size. We're calling them giants, okay? But they would definitely be above the main sequence, okay? And to the left a little bit because they are very hot, okay? The hotter end of the stars, making them blue, okay? On the other end of the spectrum, they're still very large, but they're cool stars, okay? And so these are known as the red giants, okay? So they're still large in diameter, right? They still have a large diameter, but they're cooler, okay? They're much cooler stars. So that's what we call the red giants. Let's see, let's come down the other side here, what we call our white dwarfs. So we call them dwarfs if they have a smaller diameter, a smaller surface area in there. And so if this is where the sun is, okay, here's our white dwarfs, so radius that's much smaller than the sun. And notice that they're white, okay, because they're on that sort of end of the spectral class. They're still pretty hot. They're in the white kind of region here, okay? And so they call them white dwarfs. They're very small, but very hot, okay? They actually appear very faint, so their luminosity is very low. Why? Even though they're really hot, they should be putting out a lot of energy. Their surface area is so small, right? Because their radius is so small, that makes their luminosity very low. So that's why they're down here on the luminosity end, the smaller end or low end of luminosity. So everything's kind of going together. Their temperatures and their radii, you know, that does affect their surface area, and that affects their luminosity as well. So they would be very faint, harder to see, these white dwarfs. And then over here, the red dwarfs, also very low luminosity. Their radius is very small, giving them low luminosity, but their temperatures are also very low. So that's why they're getting that red kind of color to them, red dwarfs. So we have sort of different families of stars that they're categorizing here. The blue giants, we also have supergiants, okay? And red giants there, white dwarfs there, kind of off to the lower left. You're getting very small radius down there. And then the red dwarfs as well. So a whole family of stars there. But I wanted to kind of simplify that chart just a little bit because there's a lot going on the one in your textbook or in your PowerPoints in there, but this is doing the same thing. So here's our main sequence stars, right? The sun is on that. It is a main sequence star. The sun is a main sequence star, so doing its normal star stuff. So if we have some stars that are not on the main sequence, that tells us something about their evolution. Something is happening within their structure that's causing them to go off of the main sequence. So these aren't physically moving out there in space. I mean, they are, but not in space as far as this chart goes. It just means that their position, that point that tells you where that star is located on this chart, has moved or evolved. Okay, so this will help us when we look at the evolution of stars as they evolve off of the main sequence. That's telling us that something has changed in its normal star behavior, and it also means that it's getting ready to go through a star death, okay, in various ways depending on their sizes here. So yes, we've got some blue supergiants in there, we've got the red giants and supergiants, and definitely the dwarf region, the white dwarfs and the red dwarfs over here. So get real familiar with the location of these in a sense of temperature. So where are the cooler parts of the Hertzsprung-Russell diagram? Where are the luminosity categories, low luminosity versus high luminosity? Supergiants and giants, blue or red, would be very luminous. Why would they be so luminous? Even a blue giant versus a red giant, they're both very luminous. They're way up there. Why? Because their diameters are so large, right? Making their radius large, making their surface area large. So the more surface area, the more energy getting emitted per square kind of meter there in there. And then what's going on with temperature as well. That affects luminosity. Okay, so I think it's going to take us through each one, which I kind of already said it, but in your PowerPoints, it does have this, the main sequence. 90% of all stars, these normal stars, are on our main sequence. Kind of that little slipper slide that starts in the upper left-hand kind of corner and works its way down kind of to the lower right corner of our chart. Okay, doing normal star stuff. They're all generating the hydrogen to helium, nuclear fusion in their cores, okay? All right, so now we have some giants, right? They're roughly 10 to 100 times larger than the sun. We also have supergiants that are about 1,000 times the sun's diameter. So again, radius is on here, slanting from upper right, okay, down to, upper left, down to lower right. Those are those little dash lines. Those are the radii variations, and anything along the R1 line is the same radius as the sun would be. So any star that's on that line would be the same as that. So yeah, we have some that are 100 times larger in diameter or radius, and 1,000 times, 10,000 times. We also have them smaller as well below there. Okay, the red dwarfs, so they're on the lower end of the main sequence. They're very cool, but they're also very small. So these get very low luminosities. These are very faint stars. They're really hard to see. But the red dwarfs are probably our most common star that we have. But we don't see them very often because they're so faint. They're harder to catch. Okay, low luminosity. Here are our white dwarfs. Okay, these lie in the lower left portion of the diagram. These are some of the hottest stars. They're very hot stars, so we're thinking, well, how come they're not luminous? Again, I mentioned that their surface area, their radius is so small, right? So if this is the main sequence one, here they are. their radius is so small that that's a very small surface area, which makes their luminosity low. Okay, so keep that in mind. But they're in the lower left portion of the diagram. Okay, so yeah, so the radius line and slanting like that they're talking about. Cooler stars are always fainter, and hotter stars are the same size because of that Stefan Boltzmann law in there. And so that relationship of luminosity, temperature versus surface area. Okay, so diameter versus temperature, that luminosity. Yeah. Cooler stars are always fainter than hotter stars of the same size. Okay. Stefan Boltzmann kind of law. That relationship of luminosity in there. So yeah, they're just talking about the different sizes in there. We also do a luminosity spectral classification, and this one is, it kind of gives us clues to whether or not it's a main sequence star, a giant, or a supergiant, so they kind of have them spelled out there. But it's looking at the effects of the line width on the spectrum. So we talked about the spectra, all these lines on the spectra, right? Those absorption lines, but the width of it. And so they can set up sort of this luminosity spectral classification according to the width of the lines. Notice here in your supergiant, okay, these are very narrow spectral lines. Because they're so hot, that hydrogen in there is only producing very small, narrow kind of spectral widths. Okay? Here we have a giant in there as well, and these are kind of intermediate widths. And then we have a main sequence one. Look at those. Those are much broader spectral lines within a main kind of sequence. So you can set that up according to the line width, and this has to do with what's going on with the density in the stars. So our supergiants are the least dense, okay? And so as far as you got your hot temperatures, yeah, or you could have them cool, but the supergiants, very large diameters to those, the atoms aren't packed together as closely, okay? So they're not colliding quite as frequently, and so you're getting that narrow kind of spectral line width, as opposed to, say, a main sequence star where it's not, it's more compact, and so it's more dense on a main sequence star. So you're getting the broader spectral lines, and so they can look at the spectral width of a star's spectrum, okay, take a look at it, and look at the width of that and figure out something about their densities as well. And so you can kind of sort those with some density in there. Okay. Least dense would be your supergiants, and then the most dense or more dense would be your main sequence stars in there. Okay. So yeah, I can roughly tell how big a star is. Supergiants, very narrow. Okay. And you can tell kind of how big your stars are this way. Luminosity spectral classification on that. And so then they're talking a little bit about the luminosity classes, Roman numerals. So it's another way to subdivide kind of your spectrum there of stars and put them in their luminosity classes as well. So another way to classify them. Okay. Okay, and so looking at the spectral type and the luminosity class, we can actually estimate the star's absolute magnitude, so capital M sub V, remember that. Compare this with its apparent magnitude, so little m sub V, and compute its distance. We want distance, right? Let me find where I have that little relationship here. Put that under the camera real quick of just what they were talking about there. Okay, so we can take a look at the absolute magnitude, which is something you can get from your Hertzsprung-Russell diagram, right? The apparent magnitude was the one that visually, what does it look like to our eyes, the brightness of it. So that one you can observe, okay? And from this information, we can compute the distance. So here is one other method that can be used. So from the luminosity class and the temperature of the star, its absolute magnitude can be determined. It's capital M sub V. From this and its apparent magnitude, so little m sub v, distance can be measured. So this is what we call the next rung on our ladder, called the spectroscopic parallax. This next one up on our ladder. Okay, so stellar parallax was sort of that triangulation method. Here we are, spectroscopic parallax. Does this look familiar? You might not be able to see it, but it's O, B, A, F, G, K, M, our spectral classes. So we are using the spectrum, putting that all together. So spectroscopic parallax, and we can compute distances. So one other method that we can use, and these are good anywhere from about 200 parsecs to about 10,000 parsecs. It would be a nice distance range that this would become very useful to us by looking at the star spectrum. Where is it on the Hertzsprung-Russell diagram, putting that all together and being able to get at distance. Remember that distance is a very important measurement that we need in astronomy. So yeah, spectroscopic parallax, that little relationship there. Okay, so next then, we want to figure out how much matter our star contains, and so this is going to be figuring out their masses. And we did begin to talk a little bit about that when we were looking at the sun's mass and kind of that method that they would use for that. Okay, let's take a look at that. So gravity, of course, is key in determining the masses, and we need to figure out how much mass a star contains, and if they watch that an object such as another star kind of move through the star's gravitational field. So what they do is they actually look at what we call these binary star systems, these binary stars. Okay, so you've got pairs of stars that are actually orbiting the center of mass of each of those stars. Of course, your more massive star is going to orbit closest to the center than your less massive star. So you can look at ratios of those masses and those orbits and figure something out about their masses. And so these pairs of stars, okay, orbiting each other. Now, there's a variety of stars out there, but these binary stars are pairs of stars orbiting one another. Okay, here we have the center of mass between star B and star A. You can just, they kind of tried to draw them. Star A is the smaller star, and star B is a little bit larger. Notice how star B, the larger star, okay, is, here's the radius of its orbit. Okay, it is orbiting closest to the center of mass. So the more massive star orbits closer to the center of mass. This little guy out here, star A, is going to be whipping around the center of mass there, but his radius, his orbital distance from his center of mass is larger, okay, the smaller one. So they can set up kind of a ratio of those distances, okay, radius of the larger one and radius of the smaller star, okay, radius B over radius A, the inverse of the ratio of those, and compare that to their masses, because we know that the more massive star is going to orbit closer to the center of mass. We can figure out which one is the more massive star, okay? And so then they're going to look at total masses there of those two stars, because that doesn't give you the individual masses of the the stars. So I've got a relationship that will add to many of these that we've been putting up. You won't be calculating these, okay? But it does help to see it in an equation relationship, okay? So couple things we need here. Should look familiar here. That little equation should look familiar. Okay, remember A is the semi-major axis. Semi-major axis, so that distance factor in there. And then P is the orbital period, if you remember that. This was some information that Kepler helped us with. Kepler's laws, if you remember that. P squared equals A cubed, okay, and our relationship here. And now we also can relate this to the different masses as well. So from the sizes of their orbits, okay, the sizes of their orbits, semi-major axis in there, and the orbital period, okay, P squared, the orbital period, so watching how long it takes to do an orbit around one another, they can figure out how much mass the stars contain in total. Mass of the star A, mass of star B, they can get that in total. Then they can work out the ratios for this. So combining the information with the ratio of the masses, okay, reveals the individual masses. So kind of a roundabout way. It's easier said than done, but it is a good method to get at the masses of our stars, okay? And they do take a look at various types of these binary systems. They talk about 3 types in here. This first one is a visual binary system. This is where through a telescope you can actually pick out 2 separate stars visually. Okay, so they're separately visible in a telescope, and a good example is the bright star Sirius A has a faint little companion called Sirius B, which is actually a white dwarf. So that little arrow there is a white dwarf. So there are 2 stars, and they are orbiting one another around their common center of mass. And these you can actually see separately, so you can track them. What's their orbital periods? You know, how long is it taking? What's that distance? And so they can do that and get at it. But sometimes you can't visually distinguish them. So that's kind of what they're doing, always passing through the center of mass, and so they're just observing it over the years. And the star closest to the center of the mass, again, is the most massive star. Remember that, so they can figure out that ratio. And so then they can kind of get that piece together and figure out their masses this way. Another one is here, the stars are so close together. These are called spectroscopic binary systems, where we actually have to look at the spectra and can use this premise of the Doppler effect, the shifting of these, the spectroscopic kind of binary. They're too close together, but yet their spectra will have little shifts in them. Either toward shorter wavelengths, which we call a blue shift, if you remember that, or toward longer wavelengths, we call that a red shift, because the red's kind of got the longer wavelength. So blue shifting or red shifting, and they can actually tell that these are orbiting one another, okay? And so in a binary system, out of the Big Dipper, Mizar and Alcor are actually these spectroscopic binary stars, okay? That their spectra is shifting, okay? Either blue shifted or red shifted over time, okay? So anytime the star, here's our star A, here's our star B, anytime the star is coming toward our radar or toward us, remember that's a blue shift toward shorter wavelengths. Okay. Anytime the object is receding or going away from us, okay, that's a red shift to longer wavelengths. So blue shift approaching, coming toward, red shift receding, going away. Okay, so stars orbiting each other produce spectral lines with these Doppler shifts in them. Okay, either blue shift or red shift, and they can tell. Oh, now it's coming toward us. Now it's moving away from us, and so they can figure out their orbital periods that way and the semi-major axis, and so we can figure out something about then the masses. That's another way. And a third way is the eclipsing ones. So these, we can't get a good kind of a Doppler shift from them, but what we can get is whether the light is dimming. So as one star kind of moves in front of the other, it's blocking some of the light from the other star. And so its light curve will dim just a little bit, okay? Now, let me find that picture. So an eclipsing binary system, and looking at their light curve, okay, yeah, so we got a big star here, right? And this little one starts to go in front of it. Its light's going to dim just a little bit. Once it exits in front of it, the light will go back up again, be brighter. And then it just kind of goes through this cycle, right, of star going in front of it, dimming it a little bit, star moves away from it, going up, and it can figure out again the orbital period from that, the semi-major axis from that, and there you go. So these eclipsing binary stars is another method we can use, but all together, those three kinds of binary systems can help us figure out masses. Okay, so another important physical kind of property with our masses. Okay. Okay, and so they have found, as they studied many of these binary star systems, and about half the stars are in a binary system. Our sun, you know, is kind of unique in that it is not in a binary system. So they're getting some masses, stars ranging from 0.1 solar masses, so the sun would be a 1 solar mass, so 0.1, smaller than the sun, and to nearly 100 solar masses, so 100 times the mass of the sun. And so, yeah, they've got a nice way to estimate the masses of our stars. Okay, so we're kind of putting this together to take a look at a typical stars where we've looked at a couple methods on how we're getting at the distances, the luminosity, so that total output of all manner of electromagnetic radiation, their temperatures, what's going on with their diameters. Okay, so the masses of the stars, we just looked at that. So a lot of physical properties of the stars, and we can kind of put that together and paint a picture of a portrait kind of our stars. And it does give us clues to the history of the stars in that family. Like I mentioned, some of them are evolving and toward their deaths, the various types of deaths. Okay, so the mass luminosity relation, this one, mass and luminosity, I know I already took luminosity off of there, but the mass luminosity relation, stars on the main sequence will obey this. Okay, so the main sequence, if you remember that, the main sequence stars, okay, going down like this, lower mass stars are the coolest ones, right? They're also very faint down there. But let's look at that relationship of mass and luminosity. There is an equation for that as well, but just for the main sequence stars. So mass luminosity, systematic ordering of mass along the main sequence. Main sequence stars obey it. So the more massive a star is, the more luminous it is as well. And so there is a relationship for that. massive main sequence star is, the more luminous it is. And so if you're thinking of your spectral type O stars, right? Back up here. Well, somewhere here, there it is. Your spectral type O stars, okay, would be your more massive stars, okay? And then as we kind of come down, okay, to our lowest mass stars, okay, these would be the coolest, faintest main sequence stars on there. So they're lying on the main sequence, okay? These will follow the mass luminosity. So what that's saying is luminosity is equal to the mass of your star to the 3.5 power. Okay, so the more luminous the star, the more massive the star is. Okay, the less luminous, the less massive the star is. So this does work for our main sequence stars. Okay, only. So yeah. Given the mass and diameter of a star, that average density can kind of be calculated. So once we've gotten our masses, we can take a look at density. This is another physical property, and we did kind of look at that with the sun as well. So if you remember, density, mass over volume, and volume is 2/3 pi r cubed, right? So getting that radius there. Okay. So if we can get our mass from our luminosity on our chart there, okay, really what we just need is the diameter, because we can get radius from that. Density is not too difficult of a calculation to get at. So the luminosity, the mass relation, okay, and getting at density, another physical property up there. And density does, you can get these kind of on our chart, our Hertzsprung-Russell diagram, to separate out by density. The sun's density, approximately 1 gram per centimeter cube, which is about the density of water. But again, when you're thinking of a star, you're taking an average of all the densities. Very near the core portion, central portion of the star, that's going to be your most dense region. And then as you go out, it'll become less dense, but they take an average of that. And so the sun's average is about a 1, so definitely kind of intermediate here, medium size. But the main sequence stars have average densities similar to the sun's density. So anything kind of along that main sequence star, you're going to get about the mass, the density of the sun on that. But we do set up that the supergiants and giants, they're going to have very low densities ranging from 0.1 to even 0.01 grams per centimeter cubed. And supergiants are even lower, okay? To the point where on the other end of it, we get the white dwarfs, okay? They're very small, but their density is extremely high, okay? White dwarfs are the most dense for density. So it says on Earth, a teaspoonful of this material would weigh 15 tons. So our white dwarfs are the most dense stars, okay? They lie below, of course, the sun on the Hertzsprung-Russell diagram. But density, we do see this sort of division among the stars. Most stars on our main sequence are similar to the sun, so about a 1 gram per centimeter cube. Your giants and your supergiants, very low density stars, and then your white dwarfs are very high density stars. But we got to think about our equation on here, why that would be. Let's think of our supergiants and our giants. They have a very large diameter, right? So their radius would be large. That would be this volume calculation, the bottom number in our mass over volume to calculate density. So if that's a very small number, I mean a very large number on the bottom here, you're taking a number and dividing it by a very large number. That's going to give you a very small density. Maybe our giants are supergiants. If on the other end of the spectrum we take a look at the white dwarfs, remember how small those were? Those surface area are very small, so their radius is really small, which would make the volume a very small number on the bottom. So you're taking the mass and dividing it by a very small number. That's going to give you a very large density. So think about your equation when you're thinking about the densities of these stars and how we've got sort of these three or groups of density. Okay, so, main sequence stars like the sun, kind of medium, right, for density. And then your giants and supergiants are very low density. And your dwarfs, okay, those teeny tiny, we're talking about stars though, but the teeny tiny dwarfs are very high density. Those are going to be your most dense. So these densities are actually showing us something about the stages in the life of a star. What is happening to them, because those giants and supergiants and even the white dwarfs, something's happened to those. They're not a main sequence star, which is a normal star doing its normal thing. They've evolved off of that main sequence, and so they're beginning to go through some changes that do lead to their deaths. So we'll definitely be looking at those when we talk about our star deaths. So those are many, many properties there that we were looking at. I mean, this is just a portion: mass, luminosity, density, temperatures, absolute visual magnitude, many of them that we took a look at. But here's surveying the stars, and so what we would see, and they're talking about how you do your survey could skew kind of your results. You certainly need to look at enough stars, right, to hope that it's representative in the universe there. But it's very difficult to get an honest survey because if you don't have enough, like it says, your results could be biased. Another thing that happens is our little faint stars. So the M dwarfs and the white dwarfs. So the M, of course, are the cooler, the little red dwarfs. And then your white dwarfs are down here. They're so small, right? Their radius is so small that their luminosity is low. And so those can get overlooked because they're so faint. We can't see them. And I did mention that it is thought that the red dwarfs are the most abundant type of stars. So our little red dwarfs down on this end. But they get kind of underrepresented because they're so faint, right? Even our white dwarfs, very faint. So they could get overlooked. They're difficult to find even near Earth. So they might get undercounted. The very luminous stars, yeah, so your giants and your supergiants, these up here that are very luminous, they've got these large diameters and radii, very luminous. Easier to see, right? We can see those, so maybe they're getting overrepresented. They might actually be kind of rare, but just because we can see them so easily, they might get overcounted on that. So, it could be a skew there. So we do need to look at some of these things when we survey the stars. Okay, so the night sky is a beautiful carpet of stars out there. We've got giants, supergiants, and some dwarfs. It's a very rich diversity that's out there. And they just kind of liken it to if you were out in the ocean swimming, you're probably going to catch, a lot of the sardines and the tiny things, but the whales are the ones you're going to see, right? Because they're the biggest, right? They're very rare, but they're the most luminous, so they're easiest to see, right? If we're doing an analogy to that. But the most common are probably going to be your little sardines, right? Your little red dwarf kind of things. So we set out to find the basic properties of stars, and we looked at a bunch. Distance was very important. We at least presented to you two. The first one was the stellar parallax, measuring the parallax, and then triangulation of that, and then the spectroscopic parallax as well. So using the spectra, the OBA, FG, kiss me, KM thing. So using that, so distance. And from distance, then you can get luminosity, all right? So all of these, putting the luminosities and their temperatures together gave us our diameters. And so all roundabout ways, these equations are in the back of your book. You have a math reference card if you need to look at that a little more closely. And so I'm not just pulling them out of thin air. They're there for you if you want to look at them. And then studying the binary stars gave us our masses. But what we see, the largest and most luminous stars are pretty rare. The average stars are low mass, that they're hard to see, even near kind of Earth. So why are they so different? Like I mentioned, main sequence are doing normal star stuff. Supergiants and giants, white dwarfs and red dwarfs, they're doing some other things. They're not on that main sequence. And so we need to explore the birth, the life, what normal stars do to be able to understand why these have moved off the main sequence and why they are the way that they are. And I mentioned that they're beginning to evolve off towards their deaths, and they will die in various ways depending on their different sizes. And so that will be sort of the next couple chapters that we are first going to look at the births of stars, what they're doing normally during their life, the majority of their life. They spend 90% on the main sequence, right, doing normal star stuff. And then chapter 11 will devote to the various deaths of stars. The stars are born, they live their lives, and then they die in actually some of the most spectacular ways astronomically in that. So that's sort of a synopsis here of chapter 9. I think that's the last slide, yes. So take your study guide, make sure you're looking at all the bullets and that you can gather some information for that. And certainly if you have any questions, make sure that you get with me. All right, and I'll see you next time. Thanks.